Hi, welcome to Autodesk Simulation TV. Today we're going to be talking about when to upgrade from Inventor Professional to Simulation Mechanical. Now in this overview, we're going to first start out and talk a little bit about digital prototyping, right? So again, this is really an Autodesk strategy when it comes to manufacturing in general. Taking everything from cradle to grave, from concept to creation. Now Inventor is going to play really a very key role as the centerpiece in your digital prototyping story, but we're going to be focusing on the simulation portion today, which Inventor plays some role in, but it's a little confusing as far as where that line is drawn, what Inventor can do versus what it can't. So why don't we take a little stroll down memory lane here and talk about some of the acquisitions Autodesk's made in the simulation space. So in 2005 was Solid Dynamics, 2007 was Plasitech. Those two acquisitions basically live on within Inventor Professional or Product Design Suite Ultimate today. That's your Inventor simulation. Then came the Moldflow acquisition, the Algor acquisition, and the Blue Ridge Numerics acquisition, which was the CF Design product. Now, what we're really going to be talking about today is Product Design Suite Ultimate and the Simulation Mechanical. Okay, so to focus in on those two products, this is from the Algor acquisition versus the kind of Plasitech and Solid Dynamics acquisitions. Now we can get into detail on what specifically these two programs can do. And I could go through this chart with you here, but let's be honest, it's a little difficult to go through. You're kind of straining your eyes to even see what's happening there. So why don't we break this down kind of point by point in a little bit more digestible fashion. So what can I simulate in Inventor? There's basically two things. There's static stress with linear material models and natural frequency or modal analysis. What does this really mean? Now static stress, that's going to be a baseline, simple, static, finite element analysis. That's going to basically let you take a part, lock it down in space, it can't be free floating, and put some loads and constraints on it and see how it's going to deflect or deform, right? It's got to be a static scenario, and it can only use linear materials, basically meaning nothing's going to go beyond the yield point here, or nothing's going to be something crazy like a rubber material, right? Now a modal analysis is going to let you take a look at any geometry, part or assembly, and say, how is this going to vibrate, or how is it prone to vibrate? So this is going to give you the mode shapes or natural frequencies of the system, and it's going to let you take a look at that information, and from that you can kind of extrapolate some other things that may or may not happen. Now why would we want to go beyond Inventor? First of all, we'll think about that static scenario. You can take that and go into a fatigue analysis in Simulation Mechanical. Of course you can do those same analysis types in Mechanical as you can do in Inventor, but you have additional capability beyond that, right? So fatigue analysis lets you look at a simple scenario, right? You hold something in place and you push on it or you pull on it. How many times can I do that? Can I cycle that 1,000 times? Can I cycle it 10 million times? I need to make sure this product is built to last. That's what fatigue is going to let you take a look at. Now, we talked about modal analysis that you can do in Inventor simulation. So this is going to be a baseline, natural frequency analysis, basically saying, hey, how might my part or how might my assembly vibrate? Well, using Simulation Mechanical, you can go beyond that to the point where you're actually going to be able to simulate full shaker table testing. So you can look at how's this system going to respond to a shock load, like an impulse? How's it going to respond to assorted vibrations? How's it going to respond if we attach a motor to it and shake it with a particular force? You can also look at things like thermal stresses. So we have steady and transient heat transfer, which is going to allow you to get that data, those temperature profiles, the gradients through all your part thicknesses, read that into a structural analysis, and see how much thermal expansion and thermal stress you're going to get because of it. We can also do nonlinearity. So again, these are all the reasons you would move to Simulation Mechanical. So nonlinearity is a big one, but you may be saying, what is nonlinearity? When do I have it? I don't even know what that means. Let's back up a step. Right? There's a bunch of things that can make an analysis nonlinear. The three primary is material, geometry, loads, and boundaries. right? Now what that really breaks down to, when it comes to materials, any material getting pushed beyond its yield point would be nonlinear for a simple material like steel and aluminum. Now, there's also more exotic materials, hyperelastic materials, for instance, like a rubber or a foam. Those types of things would be nonlinear pretty much from the get-go. Same with plastics. Now, there can be geometric nonlinearities as well, and that's just going to depend on the particular situation. Loads and boundary conditions would be anything that's going to change with time. So one good example of that would be contact, right? So if we drop something, its loads or boundaries are going to change based on whether or not it's contacting something else at the time. You can also do full dynamics. Again, since this is a fully momentum integrated nonlinear solver, it's going to let you take a look at different speeds, right? So one thing, something happening over a second versus over a minute, it may have different stresses resulting from that. Buckling is another thing you can do. Now there are actually two different types of buckling. We call them linear and nonlinear, right? It's just going to depend on what it is that's causing the buckling. So full system level buckling a lot of times can be predicted just using our linear solver. It's almost like a vibration type analysis actually. But beyond that, you can do nonlinear buckling, which is going to result from localized failures. Right? Anytime you have a local failure in a system, it can cause that system to buckle. So at a certain rate, right, the same amount of load causes the system to basically fully collapse. One last thing is advanced integrations. Okay, so this is something that a lot of times you may not even think of when you consider the two different products. But the simulation mechanical product just is able to integrate kind of on a higher level with some of the more advanced Autodesk solutions, such as MoldFlow. So MoldFlow is our plastic injection molding software, so you can use that to, simulate part filling analysis of any plastic injection molded part. And what's really cool about the integration is it's going to let you take as molded stresses and fiber orientation. So fiber orientation is really cool. When you inject plastic, a resin with fibers, like a glass-filled nylon, for instance, into a part, you're going to get different orientation based on how it fills that mold, right? So think about like wood grain. You're putting grain into this material, into this part with a specific orientation, which is going to greatly affect how the part carries load, how strong it is in different directions, things like that. We can pull all that data directly from a MoldFlow file, as well as the residual or baked-in stresses. When you pull this hot piece of plastic out of the mold and it cools down, it's going to warp a little bit. It's going to have built-in stresses. We can capture all that information with Simulation Mechanical. Showcase, Publisher, and 3D Studio Max, we can integrate with all of those through the export of FBX files. And Showcase, actually, we have a button directly within the software to send models straight into Showcase. Now, using software like this, here's where you're going to be able to take those simulation results and really make them pop by putting them into a high-end rendering solution, seeing how that works in conjunction with the rest of your assembly, things like that. Okay, so just to recap some of the capabilities that are really additional in Simulation Mechanical, right? We talked about the first couple here, static stress with linear materials. That is available in both packages, right? So that's what you can do in Inventor and what you can do in Simulation Mechanical. Linear dynamics, that's all your vibration. That does include the modal analysis, which is available in Inventor and Mechanical. But all the rest of the vibrations, all the shaker table simulations, that's going to be Simulation Mechanical only. Beyond that point, it's all sim mechanical. So fatigue analysis, life cycle fatigue, the buckling analysis, the steady and transient heat transfer, all the nonlinear, which includes motion, nonlinear materials, nonlinear buckling, things like that. All that's going to be available in the Simulation Mechanical package too. I'd like to thank everybody for their time and hope to see you here again on Sim TV.